Let's take a look at section 1.3, the language of relations and functions. So if you have two sets, A and B, a relation from A to B is a subset of the Cartesian product A times B. The set A is called the domain. The set B is called the codomain of that relation. Now, I want to note that the concept of a codomain is not the same thing as the concept of a range. And you might be thinking that because usually we talk about domain and range together. Range is something a little bit different. I don't want to get into the distinction here. It is something we'll talk about in a future chapter of the book, but I did just want to take a moment to emphasize that when you see codomain, do not think range. They are not necessarily the same. In some examples they are, but in general they're not. Let's look at an example. So we've got one set consisting of the elements 1, 2, and 3. We're calling that first set A. Second set B consists of the elements 3, 5, and 7. And we want to define a relation from A to B in the following way. So we have this rule, and we say that the ordered pair AB, lowercase a, lowercase b, is in the relation provided that 2a is greater than b. So that's what we check. And remember, this is a subset of the Cartesian product. So in this case, we've got A has 3 elements, B has 3 elements, so that Cartesian product has 9 elements. And if we check those 9 elements, we find that there's 3 of them that meet that condition. 2, 3, 3, 3, 3, 5. By the way, instead of saying that an ordered pair AB is an element of R, another way that that's sometimes written is ARB. Or to take a particular example related to the relation we were just discussing, we could say 2R3 to mean that 2, 3 is an element of R. We could say 1 with an R and a slash through it, 7, meaning that 1, 7 is not an element of R. And notice here that we're talking about R as a set. We're using this concept of element. And remember, it is a set. It's a subset of the Cartesian product. So, we've got this new concept of a relation, but it builds on these set ideas that we saw in the previous section. Now, this is what's called an arrow diagram. We've got the domain on the left, we've got the codomain on the right, and we've got arrows for each of the ordered pairs that are made or that make up that relation R. Okay. Now, a function is a particular type of relation. So a function is a relation with a couple other requirements. So the first one says that for every element in the domain, there's an element in the codomain such that xy is an element of f. So what that's really saying is that every element of the domain is part of some ordered pair of that function. The other condition says that for all elements in the domain and all elements y and z in the codomain, that if xy is in f and xz is in f, then y is equal to z. Let me just clarify what that's saying. It's saying you cannot have two different ordered pairs with the same first coordinate and different second coordinates. That cannot happen in a function. And if you think about how you've understood functions from other courses you may have taken, like algebra courses or pre-calculus or whatever, we've got this concept of the vertical line test or other ways of testing whether we actually have a function or not. And this is really consistent with that. It's saying you cannot have different outputs for the same input. We're looking at this a little bit differently, though, because we're talking about it in terms of sets, which is not necessarily how you may see a function defined in other math courses. So returning to our previous example, we can ask ourselves, is that a function? Okay. Remember, A was the set consisting of the elements 1, 2, and 3. B was the set consisting of the elements 3, 5, and 7. And that's important because that's relevant to checking those two requirements. So the answer is no. And it fails to meet either of the required conditions. So one way in which it fails to meet a requirement is that there's no ordered pair with a 1 as the first coordinate. And 1 is an element of the domain. There's also two ordered pairs that start with a 3 and have different second coordinates. That cannot happen in a function. So let's talk about a different relation that we're going to call F. And this consists of, it's the same A and B, same sets A and B. This relation, or in fact function, because it does meet those conditions, consists of the ordered pairs 1, 7, 2, 3, and 3, 5. And that's just the way we're defining F here. We're not giving a rule, we're just saying, here are the elements of it. And that's a perfectly fine way to define a relation or a function. Let's look at its arrow diagram. And notice this arrow diagram, from each element in A, there's exactly one arrow extending to some element in B. And that is exactly what is required of a function, that every element of the domain has some arrow, and remember the arrows correspond to the ordered pairs. So there has to be one and only one arrow from each of those elements of the domain. Doesn't matter if they point to the same place or different places, but there has to be one that originates from each of the elements of the domain, and only one. Okay, so note the arrow diagram for F is helpful in identifying it as a function. You might find that in the examples you see in section 1.3, that even if the problem doesn't ask you to draw an arrow diagram, you might find it helpful to draw one because, for example, it helps us decide whether we have a function or not. There are some other types of definitions we'll see around relations and functions later in the course, and arrow diagrams will be helpful there as well in kind of deciding whether a function has certain characteristics or not. Okay, that's it for this video. I hope you found it helpful, and I'll see you in the next one. The next topic, by the way, chapter 2, we get into logical form and logical equivalence, and I look forward to discussing that in the next video. Take care. Bye-bye.